Well, welcome back, guys, and I do hope, as ever, you and your family are keeping well. So what we're going to look at today is the next lesson on electric fields, and it's how small charged particles behave when they're put into uniform electric fields. So if you remember, electric fields put forces on charged particles. We define the electric field strength as being F over Q, the force per unit charge. So I've set up here that if a force acts on a charged particle, something like an electron or a proton or an ion, okay, it will accelerate. So if you put charged particles in electric fields, they're going to feel a force, F equals ma, they're going to accelerate. And if they remain in that field, they will accelerate and get to higher and higher and higher velocities. The acceleration, keeping it simple, should stay the same if it's in a uniform field. Okay, but they'll get faster and faster and faster, and theoretically we'll get to infinite velocities. But of course, I think you're aware that the speed of light is the limitation here. But you can accelerate small charged particles to velocities very, 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 very close to the speed of light. So this is the sort of physics you need to know to understand particle accelerators. I hope you appreciate that we're not going to accelerate neutrons in this type of system, because neutrons are neutral and therefore won't feel a force due to the electric field. So rather strangely, let's kick off with sending you off to a different video. And of course, if you've been in my classroom, you should have seen this last year, building an electron gun. So I'll put a link above to this video, and I'd like you to watch it to see how we can use an electric field to accelerate electrons to very high velocities in an electron gun. So let's kick off by looking at charged particles that are going to be put in a uniform electric field and are going to travel are going to feel a force along a field line, but they're also going to travel along that field line. So we're going to look at how they accelerate due to the force acting upon them. Okay, and that force will be, in this case, parallel to the field lines. So let's make a uniform electric field. And I think you know now what I'm going to draw. It looks like a parallel plate capacitor, but it's just parallel plates. So there's one, and here's the second one. And we'll charge this up to create an electric field between the two. So let's make the top plate negative. Okay, a lot of textbooks make it positive, but I'm going to make it negative. And therefore the lower plate will be positive. And we'll show the presence of the electric field in the gap. So if ever you have to do this, use a ruler and make sure that the electric field lines are evenly spaced to show that the field is uniform. Try my best here. There we go. Smudge the positive a little bit. So we'll put those back in, make it a bit clearer. Now, you're probably shouting at the screen at the moment, at least I hope you are, saying, FJ, you've forgotten the direction of the field. Yep, that's really important. The direction of the field is always the direction a positive charge would move. Okay. So there's our uniform electric field. And what I'm going to do, just to make this point very clear, is I'm going to put in this uniform field a negative charge. Okay, I'm choosing to do that because it's awkward. So here we go. Let's put an object in here that's negative. Okay, now there's no reason for me to draw it on a field line. I can put it here. It doesn't make any difference, okay? This whole area is full of electric field. I hope you're aware that the electric field isn't just where the line is. It's just a way of drawing the direction of the electric field and giving some representation of its shape and strength. Okay, well, it's pretty clear that that might be something like an electron. So if it's an electron, it has charge on it of minus E. Okay, 1.6 times 10 to the minus 19 coulombs, but minus that value because E is the charge on a proton. It could be something that's more negative than that, so it might have 2 minus charges or 3 or 4. You remember charge is quantized after Millikan's work. So that is going to feel a force downwards. So there's the force acting upon the charged particle. Now comes the problem, what shall we call this charge? Little q, big Q, minus E, okay? Let's just, in the general case, refer to it as charge of Q, okay? So what I want to look at here is how much work is done on this charge moving it from here to here, okay? We can also consider the force acting upon the charge, and if we know its mass and we're going to assume a rest mass here, okay, we can then work out its acceleration. And if its mass doesn't change, okay, we won't do relativity, it's not within 1/10 the speed of light, okay, the force will stay constant because it's in a uniform field, okay. The mass stays constant, so F equals ma. The acceleration will stay constant. And I think you'll be surprised by what a large value it is. So let's now look at the work done on this electron by moving it from here to here. Okay, so the electric field will accelerate it this way, will give it kinetic energy, yeah, and some things we know, okay, so we know the strength of the electric field, yeah, the electric field strength, and I'm going to use E for that, if you remember, is the volts per meter, V over D, okay, the ratio of the potential difference to the distance between those potential difference points, okay. We also know that the electric field is defined as the force felt per unit charge, F over Q. So we know using this equation here that F is equal to EQ. Okay, the force here will be equal to EQ. Now, this Q is the one we were sort of discussing. What are we going to call that Q? Well, shall we make that Q, if it's an electron, it would be minus E, the fundamental charge, the charge on a proton. Sometimes, remember, we use the letter little q because it's a very small amount of charge. You kind of need to be a bit flexible. This is the general case. So let's now look at the work done by this electric field on this negative charge. So it's going to give it energy, okay, because there's a force acting on it, accelerating it, and it will gain kinetic energy. So it's a kind of downwards particle accelerator. Do forget the gravitational field. I hope I said that earlier. Okay, we can completely forget the gravitational field at the moment because we're only looking at the effects of the electric field. Later on I might just mention it, but at the moment just home in on the only force acting downwards on this particle at the moment is the electric field, okay, or is caused by the electric field. So let's work out the energy transferred to this particle, the work done. Okay, well, we can use these two formulae, okay, because we've got the force from this formula, and we've got the distance, d, yeah, is v over e here. So let's put those two things together. So work done is force times distance. Well, the force is EQ, okay, times by the distance. Now the distance is v over e, and I think this answer won't surprise you. Okay, there go the e's. So the work done is, I'll write it backwards, VQ, or an easier way to think about it is QV, okay, And I want to just home in on this just to remind you that voltage is in joules per coulomb and charge is in coulombs. So this is in joules, or at least dimensionally, it comes out as energy. Okay, a lot of books do the work done as VQ. That's why I've written it that way round. Okay, but I like to think of it this way around personally, but it doesn't really matter. Now, don't worry too much about what this is. Is it V little e? Is it V minus little e? Okay, and you'll have to have a think what that means about the energy transfer. But more importantly, I often think about a small charge moving. Okay, so I usually give the value of charge on the object as little q. But for the sake of this maths, we'll say that this object has charge q on it. So let's do a little example now. So what I'm suggesting we try and calculate is something about a fast-moving electron. And what we're going to do is we're going to have a parallel plate capacitor, okay, with a negative and a positive plate. And we're going to fire that electron in along a field line directly towards the negative plate at that speed, okay, to 0.0 times 10 to the 6 meters per second. Well, I hope you agree that that's about 2 orders of magnitude or thereabouts slower than the speed of light, so we can forget the relativistic effects. So what I'd like you to imagine is there's the negative plate and the electrons was flying up towards it, but because the electron's negative, it will feel a force this way, will slow down and stop, and then be accelerated back down again. And what I think we might try and work out is, if it's coming in at that speed, how far will it go before it stops, okay, and turns around? So let's set up the diagram of what this will look like. So here's our standard parallel plate system. So I'm going to make this plate the negative plate. And remember, we're not going to take into account the gravitational field here. We're just looking at electric fields. Here's the positive plate. There we go. And we'll make that positive. Now, I don't need to draw the electric field in here because you're all familiar with that. We'll get our very fast moving electron. There it is. Okay. And it's moving that way. Okay, so I'm going to put a V on there to show that when it was put into the system, don't worry about how it got there, okay, but at that point, it happens to be moving vertically with that velocity. And you can see it's going to be repelled by the negative plate, so it's going to slow down. Now, what does slow down mean? Well, it means decelerate, negative acceleration, okay? So the vector of acceleration, A, will be that way, okay? If you think about it, why is the acceleration downwards when it's moving upwards? Because the force on this is downwards. It's being repelled from the negative plate at the top. So it might help by saying that way is the direction of force acting on the particle. Now, which way is plus direction on this diagram? And if you do a bit of this sort of thing at university, you'll get used to the fact that you choose and then stick with it, okay? So what I'm going to say is I'm going to define that direction as my positive direction of sort of movement, okay? Which is why this velocity here is a positive value, okay? It's arbitrary, but once you've decided on a direction, okay, pick your direction. So what we're going to do is we're going to ask ourselves, how far will this travel, starting at that speed, or velocity moving vertically, how far will it travel up vertically before it stops and then gets repelled back down and start moving towards the positive plate. So I've written down the question I'd like to answer. How far will it travel that way before stopping and turning back? And I hope all of you say it's impossible. You haven't given us enough numbers. You're absolutely right. Okay, so let's put a few more bits of data on our parallel plates. So the first thing we'll do is we'll indicate that the separation of the parallel plates, that's D if you remember. Okay, we'll give that distance. And we'll make it 5 centimetres. Okay, so the separation between the plates is 5 centimetres. And then just to be a nuisance, okay, this will seem odd to you, but it doesn't matter. Let's make this 5,000 volts. And let's make this place 4,000 volts. Okay. Now, you might say to me, well, hang on, FJ, this is positive and that's negative, so how can that be plus 4,000? Okay. I'm playing a little bit of a game here. In the exam, they'd probably just say 1,000 volts potential difference. Okay. But I'm just trying to point out that if this place is positive, then that is more negative than it. Okay. If that worries you, just imagine the top plate as negative and the bottom one as positive. But the crucial thing is, what I'm doing here is I've got 1,000 volts PD, potential difference, across the plates. Okay, so now we've got some numbers, we can work out the electric field strength in here. Okay, and if we know it's an electron, we can work out the force acting on that charge, and if we know the force on the charge and we know its mass, we can calculate its acceleration. So let's first work out the force acting upon the charge, and I think you'll be quite surprised by the number. Okay, so we know the electric field strength is in volts per meter, so V over D. Yep. And we know that the force that this will feel is EQ, because the electric field is defined as the force per unit charge. Okay, so let's have a look at the force that the little electron will feel. Well, the force it will feel will be the electric field strength, V over D, and we've got both those numbers. Yeah. So the electric field strength times by the charge on it, Q. So all we need to do is substitute some numbers in here. So let's have a go. So the force that it will feel will be equal to, okay, the potential difference. So I did this on purpose, 5,000, 4,000, so that's potential difference of 1,000. 5 kV, 4 kV, so you have to be careful with the kilo there. So 1,000 volts potential difference, yeah, divided by the distance, okay, 5 centimetres, watch that one, times by the charge on the object. Okay, well, 1.6 times 10 to the minus 19 coulombs. But remember, of course, that an electron has a negative charge on it. Okay, so if we work that out, the force acting on that tiny little electron in the electric field with that voltage and that separation is minus, okay, notice the force is downwards, yeah, minus 3.2 times 10 to the minus 15 newtons. Okay, now you might think, what? Is that really a force that will do anything? But just have a think about this. This is a very, very small force, but it's acting on an incredibly tiny mass. So I think you'll be amazed by what the acceleration of the electron is. And of course, in this case, it's deceleration. So let's now work out the deceleration of this little electron in the electric field. So again, a bit more maths here. This is simple, isn't it? That F equals ma. Okay, sort of some people describe that as Newton's second law, slightly incorrectly. The acceleration will be equal to F over m. And you can see we've been careful with our signs here. So the acceleration will be the force acting on the electron minus 3.2 times 10 to the minus 15 newtons, that incredibly small number, divided by the mass of the particle that's being accelerated. Okay, is one to look up. 9.1 times 10 to the minus 31 kilograms. Now look, that's a small number, but that's a very, very small number. So this comes out as minus 3.5 times 10 to the 15 meters quicker per second, meters per second quicker every second. Okay, 3.5 times 10 to the 15 meters per second quicker every second. It's an absolutely phenomenal acceleration. Well, why wouldn't it be? Because even though there's quite a small force on our electron, its mass is absolutely minute. Okay? So now let's use an equation of motion to work out how far it will go from its initial velocity down to a velocity of 0. So we've got the acceleration, and now all the stuff you did a year or two ago, equations of motion, SUVAT and all of that, we can use an equation of motion to work out how far it will go before it stops. Okay, now obviously you have to pick the right equation. V squared equals U squared plus 2AS. Okay, and we'll rearrange that for how far it goes. So S is equal to V squared minus U squared upon 2A. And it's worth just stopping here for a second, because this is the bit everyone finds difficult or found difficult when they were younger. The acceleration, yeah, absolutely. Okay. The distance it goes, yeah, happy with that. Okay. The final velocity minus the initial velocity. Okay, so the final velocity, well, we know the final velocity in this case here is going to be 0. So if you look at that, you'll notice there's a minus u squared. Okay, so this minus will take into account the directions we're looking at. It's quite interesting the way that works. So let's put some numbers in. So running out of space here, S, the distance it will go. Okay, well, we know v squared is 0. So u squared, what was the initial velocity? 2.0 times 10 to the 6. A bit I always forget. Square it. Okay. Divided by 2a. So 2 times by, and the acceleration, got the acceleration here as minus 3.5 times 10 to the 15 meters per second squared. Okay, so you'll notice what the u squared does up here. We've got a minus there. We multiply this out first, I would, okay, on your calculator, and know what that answer is, then know what that is. And what you should find, if you do it, is the distance it travels vertically before stopping and turning round is 5.7 times 10 to the minus 4 meters. Okay, so I just invented the numbers for this one. That's a very, very small distance. Okay, I could have changed things. I could have made the initial velocity higher. I could have made the potential difference lower. I could have made the charge. I could have made it an ion, though that would be very heavy, so that's perhaps not a good example. But this number could come out as something a little bit bigger than this, a few millimeters or what have you. But that's, very small, 0.5 millimeter or so. So even though the particle is very small and very low charged, the effect of that field is to reduce its velocity very, very quickly, stop it, and turn it back downwards. Just to finish on this one, and for the sake of consistency, you might notice I've added a little minus here for the minus u squared. Okay, so it's the u squared that's a positive number, okay, that is squared, and then it's minus u squared. So we've got a negative number on top here. We've got a negative number on the bottom here. So this all comes out as positive. So S is positive. That was our positive direction. So it has moved up, okay, 5.7 times 10 to the minus 4 meters plus, in other words, in the direction that we defined as positive. I wouldn't worry too much about that, but at university, when you do this sort of thing, you've got to be pretty consistent with which direction do you decide upon as being positive. So we've done charged particles moving parallel to the field lines. What happens now if we throw a particle in at 90 degrees to the field lines? So this is a really important experimental setup, and you'll see why in a minute. Now you can guess what I'm going to draw, of course. Our parallel plates. Okay, there and here. There we go. And again, I will choose to make the top one negative and the bottom one positive. And what we're going to do here is we're going to take a charged particle. Shall we make the charged particle negative? Okay, so here's our little charged particle. And I said to you, what we're going to do is we're going to throw this in at 90 degrees to the field lines. Okay, I won't complicate the diagram with the field lines just yet. I'll put them in a second. Okay, but here's our particle, typically something like an electron. So let's make that an electron. Perhaps it's come from an electron gun that was over there somewhere. Okay, and it's going to go into the field initially at 90 degrees. So what we can do is we can draw on this the vector that represents its velocity. And you're going to have to get used to the notation I'm going to use now. Okay, this velocity here we're going to call the velocity in the horizontal direction. Okay, I'll now draw the electric field in. And I'm not going to go mad with this. I'm just going to draw a couple of field lines just to make the point. Okay, so there's one field line, and there's another one. Purely to make the point, there's some electric field in here, and the electric field goes from plus to minus. Okay, and in the next moment or two, remember the gravitational field, we're just going to forget that. Okay, what do you think will happen? Okay, so we've got electric field lines going up like this. We've got an electron coming in that's negative. What will happen here? Or maybe it'll happen here. Give some thought to how we might complete the diagram. So I've drawn on the diagram one of the paths that the electron could take. I hope some of you appreciate that if it came in with a very low velocity, it would come down like this and hit the positive plate. With a very high velocity, it would go through and come out over here. And with the velocity that I've set, it's going to just miss the end of this plate. Oh, that's really interesting. this could be used as a velocity selector. The next thing that I want you to be clear on is that the electron is actually accelerating downwards, isn't it? Okay, it's feeling a force downwards. It's feeling a force downwards due to the electric field. Okay, and that force on it in the vertical direction, because the electric field is not changing, and the electron charge is not changing, and the electron's mass is not changing, is going to be constant. So if the force is constant, the acceleration downwards is going to be constant. Are some of you thinking what I'm thinking? A constant acceleration downwards, but no electric field across the page. So there is no force acting on the electron in the horizontal plane. So in the horizontal plane, it will just carry on at a constant velocity. And in the vertical plane, it will accelerate with a constant acceleration. Doesn't this remind you of just throwing something horizontally in a gravitational field? Now, close to the Earth, do you remember the gravitational field lines are approximately parallel? Okay, it's fairly uniform field close to the Earth's surface. And you get a parabola. And I'm not going to do it today, but I used to draw this absolutely correctly. And I used to just throw a golf ball. And if I got the entry velocity correct, okay, it would follow the line that I'd drawn on the board exactly if I drew this properly as a parabola. So I hope you can see the similarities there between the uniform gravitational field affecting a mass, and in this case, the electric field acting on this little charge here. So what we'll do is we'll have a little bit of a look at this a little bit more mathematically now. So I hope you're not too terrified of the work you did on projectile motion, but that will help with this. Okay. Quickly remind you again, horizontal velocity constant, vertical velocity always changing, and it's zero here, yeah? The vertical velocity here is zero, which is why I've only drawn on the horizontal velocity. And then when it just leaves the field, okay, so it's just, I've got to draw it sort of, okay, there's a fringing field, but let's forget that. Let's keep it simple. Let's say the field stops just at the edge of the plate. Okay, there's the object, our little electron. Okay, and it will have a vertical component and a horizontal component of velocity. Now, I hope you're happy that that one there, the horizontal component of velocity, remains the same. Obviously, it has to be done in a vacuum and all of that. And it will have a component of velocity due to the fact it's accelerated. Hope that points straight downwards. It's a bit tricky here to draw that. Straight downwards. It will have a vertical velocity as well. Okay. So what I'd like to do is I'd like to look at how long does it spend in the electric field firstly. What's its time of flight? So we're going to work out its time of flight, and just before we do, I need to point out something that's really important, and textbooks get this wrong. Firstly, an assumption, okay, that there's no field here and there's no electric field there either. Okay, yes, there's the fringing field, but let's not go there, it's a bit complicated. Okay, so let's assume that there is no field there and there. Now, if there's no field here and here, okay, the electron, once it's left this gap, the gap between the plates, the electron will feel no force. So invoke Newton's first law, it will continue at a constant velocity. That is a constant speed in a fixed direction. So why do textbooks get this wrong? Okay, well, they usually show this curvature getting bigger and bigger and bigger and bigger, which is correct. And they often have a bit more curvature going on here. Okay, it's probably going to mess up my diagram. But from what I've said, that, oh, not too bad, okay. That bit there, yep, should be a straight line, okay. So once you have it leaving the electric field, it must go at a constant velocity. I think you know what to do with these two to work out what that velocity is. yeah, because you know that this consists of a vertical component and a horizontal component. So, time of flight. Right, well, what we need to know is how far has it travelled in this gap. Okay, so we'll draw on the length that it's travelled. Now, I'm running out of colours here, so what should we do? A bit of purple. So, between there and there, this is the distance it travels whilst within the electric field. Okay, and we'll call this L. Now, this is a sort of simple GCSE. Okay, if we look at the velocity, it's the distance it travels divided by the time it took. Okay, so if we rearrange that, the time of flight in the gap, the time will be L divided by V. Okay, and we can easily do that because if we know the value of L and we know the initial horizontal velocity, remember the horizontal velocity stays the same, so we can just use this, which is a non-accelerating formula, to work out how many seconds it spends travelling across the gap, regardless of the fact that it's accelerating downwards. So we know the horizontal velocity, it doesn't change. It's VH, and it's going to be at VH at all times travelling through this system. But what's the vertical velocity going to be when it leaves the parallel plates? Well, it's accelerating. So to start off with, the vertical velocity was 0 because it was only moving horizontally. But here, it's accelerated downwards and it has a vertical velocity that is its largest value because it's only accelerating whilst it's in the electric field. It's the electric field that causes the charge to accelerate downwards, to be repelled from that negative plate. So let's see if we can work out a formula for what the vertical velocity would be. Okay, well this is quite interesting, and I think you'll enjoy this. So the first thing we need to look at is to say that we know that the horizontal velocity. Now watch my sort of crazy notation here. The horizontal velocity coming in is going to be equal to the velocity that's horizontal going out. That doesn't change. Okay. And we also know that the velocity that's vertical, the vertical velocity in, is equal to 0. So what we want to work out is what is the vertical velocity out of this system. So that's our sort of question. Okay, so I've written it down so we kind of remember what we're trying to do. Okay, well, it's accelerating. So let's home in on the acceleration. Okay, so we know the electric field strength, E, is the force per unit charge, F over Q. And there's our little Q, our electron. Okay, we also know that F is equal to ma, so that force will cause it to accelerate, and that the acceleration is F over m, or the force per unit mass. Okay, so the acceleration of this particle will be the force acting on it. Well, if we look at this equation here, F is equal to EQ. Okay, divided by the mass, m. So we've now got a formula for the acceleration of the particle in the vertical direction. So let's use an equation of motion now with acceleration in it to see if we can work out the vertical velocity just as it leaves the electric field. So did you ever believe that your equations of motion would be so important? Okay, so we want the final velocity. So the final velocity vertically coming out. Okay, so I'm going to call it the velocity that's vertical coming out. Okay, V equals U plus AT. Now, let's have a look at this. Well, U, what was the initial vertical velocity? Nothing. Okay, it wasn't moving down vertically. What's the acceleration? EQ upon M. And what's the time of flight? Oh, L upon V. So, let's put all of those together. Yeah. The vertical velocity out. Okay, this one here. So maybe I should write out there if it isn't obvious. And horizontal out of the system here as well will be equal to, well, it's naught. I think we argued that earlier on. So this is 0. There's no initial vertical velocity. Okay, plus AT. So A is EQ upon M multiplied by T, the time of flight in the system, how long it spends in the electric field, L over V. Okay, now I don't want to mess up my equation by putting little subscripts here, but remember that this V here, yeah, the V we used here to work out the time of flight is the horizontal velocity. Okay, oh, maybe I will. Maybe I'll put a tiny little h there, the horizontal velocity. Okay, but you wouldn't see that in a textbook. Okay, so by using our knowledge of electric fields and using some GCSE knowledge, and F equals ma, okay, and using an equation of motion, we've now got a formula for what the value of this vertical velocity would be. Now, if we had some numbers here, we could put numbers into this, okay? We could work out the vertical velocity. Yeah, we'd probably know the horizontal velocity. We'd probably do a previous calculation on an electron gun to work out this horizontal velocity. So if we knew that velocity and we knew this velocity, then of course we could work out what the exit velocity was coming down this way. Remember now, along a straight line. Now, there's a little bit here I just cannot resist doing, okay? And it's sort of on the verges of the specification, but I really would like to do it, okay? What would happen if this charged particle was moving at the same horizontal velocity, but it was twice the charge, okay? So it had a charge of 2e on it, or minus 2e, okay? Let's not worry about what that is. Okay, we're not going to change its mass. Just imagine it has twice the charge. Well, if it has twice the charge, it's going to feel twice the force, and it's going to bend down more. Okay. What would happen if it was uncharged? Straight through. Okay. Now, here's where it gets interesting. Okay. Imagine that this was a particle that was, let's say, the nucleus of an atom. Okay. And let's say something like uranium. Okay, now I'm massively oversimplifying here, but just to give you the idea. Okay, now imagine you take that uranium, 92 protons, and you completely ionize it. Okay, so you've now got uranium particles here, which will have a charge on them that is plus. Okay, so in the case of those, they would come in and bend upwards. Okay, it doesn't really matter. Now, if they were all the same charge, they have to be if they're completely ionized. Okay, so you completely removed all of the electrons. Okay, they would be 92 plus. And again, this is not quite what happens in reality, but it's easy to explain it like this. Fire in your uranium ions, and what you'll notice is some of them will bend up through a large angle. Some of them will bend through slightly smaller angles and some will bend through even lower angles. Now that doesn't make sense because they're all the same charge. So if they're all the same charge, then they should all bend through the same angle. Okay, because they're positive, they'll bend upwards. So there's only one thing that can change. The ones that don't bend as much don't like having their direction changed. Okay? In other words, they're heavier. They have more mass. Now, if you think about that, I think you can see where I'm going here. This is a system that could be used to separate masses of isotopes. Okay? It has actually been used for that, though there are better ways of separating isotopes of uranium these days. Okay? So imagine firing in some ions of uranium, and they're all the same charge. We're making them all the same positive charge. The heavy ones will bend slightly and can be collected here. The lighter ones will bend more and can be collected here. And the even lighter ones will bend more and can be collected up there. So you will get 235, 236 if it was to exist, 238. Okay? In other words, you will get the isotopes separated. And what this is doing is it's producing a spectrum up here of all the different masses, with the ones that are heaviest bent least, okay, and the lightest ones bent most. What I've shown you there is a really clever device. It's a mass spectrometer. So that's a useful bit of work we've done on electric fields. It's really quite beautiful to see this happening. If you can actually see charged particles being deflected within electric fields. Hold up for the physics later on when you do it with magnetic fields. Okay, but what I'd like you to do in a minute, and I'll put a link above, assuming it'll allow me to put a second link in, or I'll put it right at the end. Okay, I'll put a link to a YouTube video of mine on electron deflection and electric fields. And I'll set up the apparatus in the laboratory that looks just like this, and I'll show you electrons being deflected by an electric field and what happens when we change the potential difference on the plates. I think you'll enjoy that one. So perhaps now go off and have a look at that video. So I do hope you found that lesson on electric fields useful and you feel you've got a really good understanding now of how charged particles are deflected in electric fields. We're almost at the end of this topic. I think I've probably got one more film to make. Anyway, I'll be making that soon and I look forward to seeing you then.